Okay, let's dive straight into one of physics' biggest, maybe the biggest remaining mysteries. It's a fundamental question. Is gravity quantum?
It really is the question, isn't it? Because, we've got quantum theory, this amazing framework describing three of the four fundamental forces brilliantly. Electromagnetism, the weak and strong nuclear forces.
Right. Everything from light to atoms holding together, radioactive decay, it's all quantum, probabilistic, discrete packets of energy.
Exactly. They fit perfectly, well, nearly perfectly into the standard model, mediated by particles. But then there's gravity. Einstein's general relativity describes it beautifully as space-time curvature on the grand scale, but getting it to mesh with the quantum rules. That's where we hit a wall.
A huge wall. No proven quantum theory of gravity. And the real kicker has always been, how do you even test it? Experimentally, I mean. Theories are one thing, but actually checking in the lab.
It's been incredibly tough. Loads of theoretical ideas, sure, but a clear experimental path, not so much. Until, maybe now, there's some really fascinating work coming out of MIT.
Ah, yes. This is the team using techniques from, well, totally different areas of physics, right?
Exactly. They're taking laser cooling, something usually for chilling atoms down to almost nothing, temperature-wise, and applying it to a torsional oscillator, which is, a classic tool from gravity research.
Okay, so smashing together atomic physics and gravitational physics tools, that sounds ambitious.
It absolutely is, a real hybrid approach. And that's what we're diving into today. We want to unpack why this quantum gravity thing is so hard, look at this clever new experimental angle, and explore what it might mean for finally answering that big question.
So let's go back to that core puzzle. Why is gravity so hard to test, experimentally, at the quantum level?
Yes.
You mentioned it's the odd one out, theoretically.
Well, a huge part of it is just how incredibly weak gravity is compared to the other forces, especially down at tiny scales. Think about it. You lift your coffee cup, you're easily beating the gravitational pull of the entire planet Earth.
Right. Compared to, say, the electromagnetic force holding that cup together, gravity's minuscule.
Orders and orders of magnitude weaker. And quantum effects usually pop out when forces are strong, or when systems are really small and isolated. Gravity is just feeble at those scales where you expect quantum weirdness to show up directly.
Okay, weak force. So how do you even begin to look for its quantum signature?
That's the crux. You'd probably need to see tiny gravitational interactions between objects that are themselves behaving quantum mechanically. And Dongchul Shin, who led this MIT study, really nailed the challenge. He said, you need systems that are massive enough to feel gravity, yet quiet enough, quantum enough to reveal how gravity interacts with them.
Massive enough, but quiet enough. That sounds like a paradox right there. Big things usually have lots of thermal energy, right? They're constantly jiggling around.
Exactly. That thermal noise, that classical motion, would totally drown out any subtle quantum gravitational effect you might hope to see.
So you need something heavy enough to have a gravitational pull you can measure,
Yeah.
but somehow chilled to the point where its own quantum fuzziness is the main thing left.
Precisely. Cool it way, way down. Quiet the classical world to hear the quantum whispers. And then, ideally, see how two such objects interact purely through gravity. It's a monumental experimental task.
Which leads us perfectly to their approach. Bridging these two worlds. Let's talk about the gravity tool first, the torsional oscillator. What's the story there?
Right. The torsional oscillator or torsion pendulum, it's actually a beautifully simple concept. Basically, a weight hanging from a very thin wire or fiber, free to twist. And they have a long, long history in gravity research.
How far back are we talking?
We're talking Henry Cavendish, 1798. He used one to make the first real measurement of Newton's gravitational constant. G.
The experiment that weighed the Earth.
That's the one. And since then, variations on that theme have been workhorses for precision gravity tests, checking the inverse square law, looking for weird new forces, refining G. They are just incredibly sensitive to tiny twisting forces, tiny torques.
Okay, so a classic proven tool for measuring very weak forces on a macroscopic scale. Now, laser cooling, that's the other side of the coin.
Completely different neighborhood, physics-wise. Laser cooling really took off in the 80s. It's all about using lasers tuned just right to zap atoms and slow them down.
Slowing their thermal jiggling, right? Getting them super cold.
Unbelievably cold. Microkelvin, even nanokelvin, fractions of a degree above absolute zero. It lets you do amazing things like build the super precise atomic clocks you hear about.
Okay, and people have used it on tiny mechanical things too, like nanoscale drums.
Yeah, over the last decade or two, that's become a big area, cooling tiny cantilevers or membranes down towards their quantum ground states.
But the MIT team, they're doing this to a torsional oscillator, one of those Cavendish-style things. Those are much bigger, aren't they?
That's the key innovation. Yes, typically centimeter scale, orders of magnitude bigger than atoms or those nanoscale gadgets. Applying laser cooling directly to something like this, a macroscopic torsional system. That's the novelty.
Wow, so taking this like ultra-precise quantum control technique and aiming it at a classic gravity measurement tool.
Exactly. Merging the fields, creating this hybrid platform. The explicit goal, as Shin mentioned, is precisely to build systems massive enough to have a decent gravitational presence, but that you can then cool down, quiet down with lasers until their quantum nature starts to dominate.
Okay, concept sounds brilliant, very clever. What did they actually manage to do in the lab? What's the result in their paper?
So the paper in Optica reports the first successful active laser cooling of one of these centimeter-scale torsional oscillators.
Active cooling, meaning they're measuring its jiggle and pushing back with light?
Pretty much, yeah. It's a feedback system. And the result, they took it from room temperature, about 300 Kelvin, all the way down to 10 millikelvins.
10 thousandths of a Kelvin.
Yeah.
For something centimeter sized, that sounds significant.
It is. Getting an object that relatively large, that cold, using just laser light is a major step forward.
Okay, but cooling with light exerts pressure, pushes things. To cool it effectively with feedback, you must need to measure its tiny twists with insane precision first, right? How'd they manage that?
Ah, yes. This is where another really clever bit of optics comes in. It was essential for the cooling. They used something called a mirrored optical lever.
Optical lever. Okay, I get the basic idea. Shine a laser off a mirror on the thing. A tiny tilt makes the reflected spot move a lot further away, magnifying the motion.
That's the basic principle, yeah. A light beam as a super sensitive pointer for angles. Very common technique.
But you mentioned noise issues earlier. Things shaking, the laser beam itself wobbling.
Exactly. That's the big limitation of a standard optical lever. Air currents, vibrations, maybe imperfections in the laser or optics. They all make the beam jitter. And that jitter, when it hits the detector, looks just like the oscillator itself is moving.
Ah, so the measurement tool itself adds noise that looks like the signal. That would kill your sensitivity, especially if you're looking for tiny motions near absolute zero.
It absolutely does. It sets a limit. So their solution is this mirrored setup. It's ingenious. They actually use two beams from the same laser.
Two beams. Okay.
One beam does the standard optical lever thing, bounces off the oscillator's mirror, picks up its motion plus any jitter. The second beam takes a different path. It reflects off a special mirror called a corner cube.
A corner cube, like the reflectors on a bike.
Sort of, yeah. It has the property of sending any incoming light beam straight back exactly parallel to where it came from, even if the corner cube itself wobbles a bit. So this second beam picks up all the same laser jitter as the first beam.
But not the oscillator's motion because it doesn't hit the oscillator's mirror in the same way.
Precisely. Then they combine these two beams back together at the detector. And they do it in a way, using optical interference, that makes the common jitter signal effectively cancel itself out.
Wow. So the jitter subtracts itself, leaving just the real signal from the oscillator twisting.
That's the essence of it, like using one beam as a real-time reference to clean up the other.
That sounds incredibly powerful. What did it actually do for their measurement?
The effect was huge. They reduced the measurement noise by a factor of 1,000.
1,000 times quieter measurement.
Yeah. It let them measure the angular wiggles of their oscillator with, as they put it, extreme precision. They achieved a sensitivity that was actually almost 10 times better than the oscillator's fundamental quantum limit.
Wait, better than the quantum zero-point motion? The absolute minimum wiggle allowed by quantum mechanics itself.
Better than the size of that wiggle, yes. Meaning they could resolve thermal motions much, much smaller than that quantum floor. Even though the oscillator itself wasn't yet at its quantum ground state temperature, they could measure its remaining thermal jiggling with far greater precision than that quantum limit.
Okay, I think I get it. The measurement was quantum limited in precision, even if the object wasn't yet quantum limited in its actual state.
Exactly. And that super-sensitive measurement, as Dongshil Shin pointed out, was the key. It made it possible for us to cool the system down to just 10 millikelvins using laser light. They could see the motion clearly enough for the feedback cooling to really grab hold and work effectively.
Okay, so 10 milliK is impressive, and the measurement precision is incredible. But it's not quite the true quantum ground state yet. where the object itself is behaving purely quantum mechanically.
That's right. 10 milK is cold, but for an oscillator like this, the true quantum ground state where only that 0-point energy remains is likely colder still. Reaching that actual ground state is the next big milestone.
How do they plan to get there? What's needed?
They basically need to strengthen the coupling between the laser light and the oscillator's motion to pull out thermal energy even more efficiently. They mention things like using optical cavities.
Cavities, like trapping the light between mirrors so it bounces back and forth, interacting with the oscillator many times.
Exactly, amplifies the interaction. Or potentially exploring different ways to optically trap the oscillator itself, which might offer more cooling power.
And if they can reach that ground state and get really good control, what's the ultimate dream here? What does this unlock?
This is where it gets really exciting. The ultimate goal, the potential holy grail, is to use systems like this for experiments where you have two such oscillators, both cooled near their ground state,
Okay.
interacting only through gravity.
Only gravity. You'd have to shield everything else, electromagnetism.
Oh, absolutely. That's a huge challenge in itself. But if you could achieve that, two macroscopic quantum objects talking to each other just via their gravitational pull, then you have a platform to directly test if that gravitational interaction follows quantum rules or not. Does gravity entangle? Does it transmit quantum information? These are the kinds of questions you could finally start to probe experimentally.
It really strikes me how much this relies on bridging different fields. It's not just pure physics theory, is it?
Not at all. Shin emphasized this too. It's fundamentally interdisciplinary. You need the deep physics understanding, sure, relativity, quantum mechanics, but you also need serious hands-on engineering skills.
Like actually building these incredibly delicate setups.
Exactly. System design, knowing how to do nanofabrication perhaps for certain components, high-precision optics, sophisticated electronic control systems. It's a huge mix.
A lot of different expertise needed in one team.
Definitely. And Shin mentioned his mechanical engineering background was actually really helpful, providing that broad base to connect the theory with the nuts and bolts of building and running such a complex experiment. It really shows how tackling these frontier problems often means bringing very different skill sets together.
It's an amazing story connecting 18th century experiments with cutting-edge quantum tech. For anyone listening who wants to read the actual paper on this cooling result?
Yeah, it was published in the journal Optica. The title is Active Laser Cooling of a Centimeter-Scale Torsional Oscillator.
And the publication date?
April 19th, 2025. Lead author Dongshel Shin and other authors from MIT's Quantum and Precision Measurements Group, Vivek Sudhir, Dylan Fife, and also from the University of Utah, Tina Hayward and Rajesh Menon.
So wrapping up, this work feels really significant. It's like they forced open a new window experimentally on one of the deepest questions out there.
Absolutely. By combining these tools in such a novel way, they're pushing into territory that just wasn't accessible before. Taking quantum control, developed for the smallest scales, and applying it to systems massive enough to potentially feel gravity's quantum effects.
And just think about the implications down the road. Imagine if experiments like this, maybe building on this work, could finally definitively show that gravity is quantum. That would be, well, monumental, a huge step toward that unified theory of everything.
Or, equally profound, what if they show it isn't quite quantum in the way we expect? That would send shockwaves through physics, force a complete rethink.
Or maybe, stepping back, just consider the power of that approach itself. Taking a tool from Cavendish's time, combining it with lasers from the late 20th century, that kind of cross-pollination between fields, that willingness to connect seemingly unrelated areas, that might be one of the most important engines for future breakthroughs, tackling problems that have stumped us for generations. Something to think about.